The standing wave conditions resulting from open and short-circuited loads must usually be avoided in working with transmission lines. However, with 1/4 and 1/2 wavelength transmissions, these open and short-circuited loads can be used as resonant or reactive circuits. In this lesson, we'll discuss more about transmission lines used as circuit elements and we'll discuss microstrip and straight line. Consider the shorted 1/4 wavelength line shown in the figure. At the end, at the load end, voltage is zero and current is at maximum. But 1/4 wavelength back at the generator, the voltage is maximum and the current is zero. To the generator, the line appears as an open circuit or at least a very high impedance. The key point here is that condition exists at only one frequency, the frequency at which the line is exactly 1/4 wavelength. Because of this frequency sensitivity, the line acts as an LC tuned or resonant circuit. In this case, a parallel resonant circuit because of its very high impedance at the reference frequency. With a shorted 1/2 wavelength line, the standing wave pattern is like that shown in the illustration. The generator sees the same conditions as at the end of the line, that is, zero voltage and maximum current. This represents a short or a very low impedance. That condition occurs only if the line is exactly 1/2 wavelength long at the generator frequency. In this case, the line looks like a series resonant circuit to the generator. Similar results are obtained with an open line as shown in these figures. To the generator, a 1/4 wavelength line looks like a series resonant circuit, and a 1/2 wavelength line looks like a parallel resonant circuit, just the opposite of the shorted line. The next figure is a summary of the conditions represented by open and shorted lines of lengths up to one wavelength. The horizontal axis is the length in wavelengths, and the vertical axis is the reactance of the line in ohms, expressed in terms of the line's characteristic impedance. The solid curves are shorted lines, and the dashed curves are the open circuit lines. For example, consider a shorted 1/8 wavelength line. The horizontal divisions represent 1/16 wavelengths. So 2 of these represents 1/8 wavelength. Assume that the line has a characteristic impedance of 50 ohms. At 1/8 wavelength, on the left hand, the reading is 1. So let's apply what we've learned so far. How could a capacity reactance of 150 ohms be created with the same 50 ohm line? First, locate the 150 ohm point on the capacity reactance scale. Since 150 divided by 50 is equal to 3, the 150 ohm point is at x sub c equal to 3. Next, draw a line from this point to the right until it intersects with the two of the curves. Then read the wavelength from the horizontal scale. A capacitive reactance of 150 ohm using a 50 ohm line can be achieved with an open line somewhat longer than 1/32 of a wavelength, or a shorted line a bit longer than 9/32 of a wavelength. at low frequencies, just below about 300 MHz. The characteristics of open and shorted lines discussed in the previous sections have little significance. At these frequencies, the lines are just too long to be used as reactive components or as filters and tuned circuits. However, at UHF, that's 300 to 3000 MHz, and microwave frequencies, that's 1 GHz or above, the length of a one-half wavelength is less than 1 foot. The values of inductance and capacitance become so small that it is difficult to realize physically with standard coils and capacitors. So, special transmission lines constructed with copper patterns on a printed circuit board called microstrip or strip line can be used as tuned circuits, filters, phase shifters, reactive components, and impedance matching circuits at these high frequencies. A microstrip, a microstrip is a flat conductor separated by an insulating dielectric from a large conducting ground plane, as you can see in the figure. A microstrip, a microstrip is usually 1/4 or one-half wavelength long. The ground plane is the common circuit common. This type of microstrip is equivalent to an unbalanced transmission line. Shorted lines are usually preferred over open lines. Microstrip can also be made in a two-line balanced version as you can see in the next illustration. The characteristic impedance of microstrip, as with any transmission line, is dependent on its physical characteristics. It can be calculated by using the formula shown. The dielectric constant of popular FR4 fiberglass PC board material is 4.5, while the value of dielectric for Teflon is 3. For example, the characteristic impedance of a microstrip with the dimensions h is equal to 0.0625 inches, width of 0.1 inch, and thickness of 0.003 inches using a dielectric of 4.5 with this formula will result to 53.9 ohms. Meanwhile, a strip line is a flat conductor sandwiched between two ground planes as shown. It is more difficult to make than a microstrip. However, it does radiate as microstrip does. Radiation produces losses. Even tinier microstrip and strip lines can be made using monolithic, thin film, and hybrid IC techniques. When these are combined with diodes, transistors, and other components, microwave integrated circuits or MICs are formed. To summarize, if the line length is less than 1/4 wavelength at the operating frequency, the shorted line looks like an inductor to the generator. If the shorted line is between 1/4 and one-half wavelength, it looks like a capacitor to a generator. All these conditions repeat with multiples of 1/4 or one-half wavelength for shorted lines. For open lines, it's just the opposite of shorted lines. If the line is less than 1/4 wavelength, the generator sees a capacitance. If the line is between 1/4 and one-half wavelength, the generator sees an inductance. These characteristics repeat for the lines that are some multiples of 1/4 or one-half wavelength. We've touched on how to apply this concept in making a reactive circuit out of a 50 ohm line. And there are also special transmission lines called microstrip and strip line, which can be used as tuned circuits, filters, phase shifters, reactive components, and impedance matching circuits.